In this video, I'll show you how to control an inverter in ABC coordinates. So it's a single-phase inverter, so that means that we only have the A coordinate, but it's still stationary. So if you're not familiar with an inverter, a simplified model of it looks like this. So it's basically a voltage source behind an inductor. So this would be the real inverter that we have, but you can see that we can simplify it by adding a voltage here that the inverter generates. So if you want to understand more how this conversion to the simplified model works, go ahead and watch my other video on that. So basically, we want to control the current. So this is a block diagram for the controller of an inverter. So you can see that here is the current controller. So it takes in the reference current and then the actual current. And then it generates a reference voltage for VC, which is the voltage that we want to apply. So basically, what we want to do is that we want to find the voltage we want to apply here in order to make this current become equal to the reference current. So that is basically how we do it. So in order to design this current controller, we need to find a model for the voltage. So we can do that by looking at a voltage loop here. So if we use KVL, we have that VC is equal to the voltage over the inductor, which is VL, and then plus the voltage coming from the grid, which is VAC. So we can rewrite this inductor voltage as the inductance multiplied with the derivative of the current. So here we have a model for the converter voltage. So what we do is that we use this as a feed forward. So when we design controllers, we can, for example, choose a PI controller. We would have VC ref is equal to PI controller, which is based on the error term that we have, which is the reference current minus the actual current. So we have I just call it IREF, and then minus IC, which is the measured current. However, the problem with this is that this is oscillating a lot, and a PI controller struggles with following a sinusoidal signal. So what we're doing is that we add a feed forward such that the PI controller doesn't need to generate the sinusoidal signal. We have the sinusoidal signal here in the feed forward, and then this PI controller just corrects for that in order to get the current that we want. So this here is what we call the feed forward. So now this got a little bit messy, but if we go down here, you can see that this is the equation for the converter voltage. Then you can see that we have here the feed forward term, and then the PI correction, which just corrects the value for VC such that we get that the reference current is equal to the measured current. And now the problem with this is that we are taking the derivative of a signal which is noisy. Because when you measure a signal, you will always get some white noise in it. And yeah, you can filter it, but usually this term here is rather small, so it doesn't really matter because the inductance is relatively low and the derivative of the current is relatively low. So just removing this term entirely simplifies this a lot. However, if you have a large inductance or the current is very large, which leads to a large change in current as well, I would add this term here. But I think in general, you can just remove it because taking the derivative of a noisy measurement adds noise, and if you filter it, you add delay. So I will just in general recommend to remove it, but if it's significant, have it. So you can see here that we've removed the derivative term. So if we do that, you can see that we get this type of a controller. So you can see that I have a D here instead of a C. That is wrong. It should be C here. So I'll correct that for the course. That is because it's taken from the DQ. So this is a part of a course about how to control bidirectional inverters. In my next video, I will show you how to make a simulink model where you simulate this.